Let's now talk in more detail about each of the individual terms in our energy balance. And we're going to begin with the left-hand side by talking about the dE term, the change in energy. Now, typically, when we talk about energy in thermodynamics, we're actually going to split it up into three different contributions. So dE, we're going to say, is going to be equal to the sum of du, dEk, plus dEp. All right, and so to define what these three things are on the right-hand side, I'll actually start at the end. And so this dEp, this is known as a change in potential energy of our system. And so by potential energy, what we talk about is the influence of any force on our system due to an external field. And typically that external field, one easy example that you could think of is gravity. All right? And so potential energy would just most likely be talking about the effect of gravity on the energy in our system. The middle term here, this refers to the change in kinetic energy. And so for kinetic energy, what we're talking about is translational motion of the center of mass of our system. Center of mass of entire system. So basically, if we think of our system and the boundaries along with it, the kinetic energy would be describing the essentially the energy associated with the speed of how fast that system is moving. All right, and so kinetic energy and potential energy, those are two concepts that you focused on in your Physics 1 class. In this thermodynamics class, we're going to spend more time, honestly, talking about this du term. And this du term, as you remember from MEB1, this is the internal energy. All right? And this internal energy, that's more associated with not, the entire system and its boundaries. It's more concerned with these microscopic movements of the molecules in our system. All right, and so that's what internal energy refers to. To illustrate this idea of internal energy more concretely, I want to go over an example with you. Okay? And the example we're going to go over is going to be a balloon filled with helium gas. Okay? All right, and so for this balloon, all of you have seen a balloon before. Kind of looks like that, with a little string at the bottom. And so this balloon that we're going to be talking about is going to be filled with helium gas or helium molecules. Helium molecules, it's a diatomic molecule. And so it's going to have two atoms here that are connected by a bond. So this bond is kind of looks like a spring. Okay? And so our balloon is going to be filled with multiple helium molecules, not just one, not just two, but more like 10 to the 23rd, or Avogadro's number of helium gas molecules. Now, with these helium gas molecules, they're not just staying in place, but they're moving in all different types of ways. And that's what the internal energy is going to be describing. And so the different types of ways that these helium molecules can be moving, one way is that the entire molecule just moves from one spot in the balloon to another spot here. And so that type of movement is what we would call the translational motion of the molecule, or the center of mass motion of the molecule. Right? And so you could kind of think of it similar to that kinetic energy term DEK in our energy balance. But rather than talking about the movement of the entire system, of the entire balloon, what we're talking about is just the movement of an individual molecule. All right? And so that's one different type of way that the molecule can move around. The other type of way has to deal with the little bond that we have here. I mentioned that the bond between the two atoms is like a spring. And so this bond, it's not like a rigid sort of material. It's not like a steel rod or anything. It's more like a spring that could compress either inward or recoil back outward. And so these molecules can kind of sort of act like an accordion, where they squeeze in and out all the time. Right? And so that's another type of movement that the internal energy is going to be characterizing and describing, these sort of vibrational motions. The other thing we can consider is, because helium is this diatomic molecule, is the molecule itself could actually just be spinning around or rotating around some sort of axis. So it could be spinning through space. And so when we talk about microscopic movements, we also need to consider the rotation of the molecule. And the last sort of microscopic movement I want to talk about isn't so much a type of movement, but it's more kind of describing how the molecules see each other. Or in more general terms, we could think about the interactions between molecules. And so as you learned in your general chemistry course, and even in physics 2, molecules could either interact with each other either in a repulsive manner or in an attractive manner. And the characteristics of this attraction, these will also be described by the internal energy as well. All right, and so we have 4 different types of microscopic movements that we need to consider. And all 4 of these types of microscopic movements, this is what's captured in our internal energy term. And because these microscopic movements are happening at the microscale, that means we really can't see them with our naked eye. But we still can get a sense of what the internal energy of a system is through another one of our senses. Specifically, we get a measure of the internal energy of a system by looking at its temperature. What's the temperature of that helium gas? What's the temperature of the entire balloon? And that's because temperature, it characterizes the speed or frequency of these microscopic molecular motions. Alright? And so we'll talk in more detail about how the internal energy is directly related to this temperature. But for now, I just kind of want to talk in general terms and just say that internal energy is a function of temperature, and that molecules will move or vibrate more quickly or faster as the temperature increases. Alright? And so when we think of internal energy, I want you to think of these 4 different types of molecular motions, and that the speed of these molecular motions is going to be directly related to whatever the temperature of the system is. Alright, so that's internal energy. But another sort of useful quantity we could define, or that we have defined in MEB2, is enthalpy. And we abbreviate enthalpy as H. And enthalpy is mathematically defined as the sum of the internal energy plus pressure times volume. Right? So it's the sum of internal energy plus the pressure and volume of the system. Your enthalpy can be calculated for both closed and open systems. So it doesn't just apply to open systems, it applies to any sort of system. Right? And so, once again, it's the sum of internal energy and any sort of work that involves changes in pressure or volume. So PV work. We'll talk more in detail about what exactly enthalpy physically means. But the utility of defining this enthalpy term is whenever we're dealing with closed systems, if we're able to calculate or estimate the enthalpy of the system, that's automatically going to account for mechanical work and if we're dealing with open systems, if we calculate the enthalpy, that's automatically accounts for flow work in our energy balance. So essentially, by using enthalpy rather than directly internal energy, it helps simplify our energy balance analysis.